Hi, welcome back. We're going to do 315 and as many as we can get through, and I want to talk about this question specifically because the one right next to it, kind of, if we understood this one, maybe this question might be better to understand. So it says two people, Miss Woods and Miss Bryan, are vegetable gardeners. They want to use different fertilizers and they're trying to figure out which fertilizer works best. So they're using two different gardens, which is a little suspect. We used 4 different fields here, but we used blocking to help make sure that we knew we could isolate the difference of the field. They didn't do that here, and that's one of the big problems. So as we see here, they'd like to say, aha, is it the fertilizer that's getting bigger tomatoes? Because this is a p-value that we would like to use, and we do think that'd be convincing evidence. So let's take a look. So if you take these notes, you think about garden number 1, and it would be nice to use the treatment of the fertilizer, 2 different types of fertilizer, 2 different types of fertilizer. And then if both of the gardeners had bigger tomatoes in this part, then we could start to think, that was convincing evidence that I think it is this fertilizer. But the fact that one gardener used one fertilizer and one gardener used another fertilizer, that we've got these soil conditions, the fact that there's 2 different gardens, and forget even just the soil conditions, maybe each garden gets a different amount of sun every day, gets a different amount of water every day. So we use blocking to help control the situations that we can't control. And that would have helped here if we would have used the 2 types of fertilizer in both fields. So we look here, D is the right answer because the soil condition would be a confounding variable and a potential issue. Okay, next question. We have an EPA that's charged with monitoring emission. So we kind of have to assume people are not breaking the law. Our H sub O is that they're meeting that level of 5, but they are being suspicious if they have more. Suppose that a particular industry, the acceptable emission has been set at no more than that. So if we believe that someone is breaking the law, that's our alternate hypothesis. And they'd like us to describe what would be a type 2 error. So that can actually be fairly easy if you use the posters in the room. The posters in the room state, it says, a type 2 error means I walked through door number T, which means we failed to reject the null hypothesis. But an error means, oops, I should have rejected it. We don't have sufficient evidence to show that mu is greater than 5, but we were right all along. Our hunch was correct. So when we look at our answer choices, we notice that E fits here perfectly. It's when the EPA fails to find convincing evidence when in fact they were correct, that person was exceeding the acceptable limits. So this happens actually quite a bit, where we had some amount of evidence in our sample that mu was greater than 5. It just wasn't sufficient enough evidence. Okay. And as we know, we can increase the power of the test. Maybe you could do another test. Don't give up. If you have a hunch, keep going. Okay. Question number 17. 17 states, which of the following is false? Okay, so the first one says measure of center alone does not completely describe the characteristics of the data set. And that, I would totally agree, is a true statement. Here's a picture to explain that. So look at both distributions, the yellow one, which is uniform, and this one, which looks normal. Both have a center right there. Yet, measure of their center alone does not completely describe the characteristics of this data. Okay, now looking at B, it feels like this relates to a question we've already had. If the original measurement are in inches, converting them to centimeters will not change the mean or standard deviation. I can't help but going back to a problem I already talked about. The part that's unchanged when you change units is R. But when you change units, you definitely change mu. And let's think about that. Let's say I measured a whole bunch of inchworms and their average length was 5 inches long. If I'd like to convert my study to feet, now my average length is 0.41 feet long. Haven't I definitely changed my mean? Absolutely. And the same would be true if I changed from inches to centimeters. But again, it's quite a bit easier to change from inches. It's probably not easier, but there you go. Hopefully I convinced you. All right, question 18. It says a 96% confidence interval was performed to trying to find out what percent of people were unemployed. So a 96% confidence interval produced the interval 7 to 10%. So that's a pretty low unemployment percentage. And we could also think of it as 0.85 plus or minus 0.015. That's saying the same thing. So that's pretty low, 8.5% unemployment, and we could, we're not sure. So what does it mean to produce a confidence interval? Well, this picture actually reproduces what we went through in class. So if you look at it, if the center really truly is the center we found, 0.085, then I cast a net. Oops, I captured it. I cast a net, an interval, and I captured. Cast it, captured. Cast and captured. Cast and captured. Cast and captured. Cast and captured. I cast a whole bunch. And in fact, 11 out of the 12 intervals I created captured the true mean. So if I was just, kind of experimentally trying to figure out this confidence interval percentage, that's about 92%. If I threw out 11. So when they're saying they did a 96% confidence interval, they're saying that if they did 100, 96 of them would capture it, and about 4 of them would not capture it. And that's exactly what our script says. So practice maybe writing out the script so that you won't forget it. About 96% of the intervals from 0.07 to 0.10 capture the true proportion of the unemployed in the city. And this helps us think about what's happening in the calculator. All right, question number 19. A large toy company introduces a bunch of new toys for the product line. The company wants to predict demand, and they're going to call that Y. They are going to use X to predict Y, and X is the awareness of the product. They took a random sample of 65 products and got a correlation value of 0.96. That's a really high correlation value. That means their prediction model is almost perfect, which would be 1. Okay, so what would be the correct interpretation of that value? In fact, answer number E is our script. This is exactly our script when we can take our correlation factor and square it. So when we take our correlation factor and we think about what's happening, we're thinking the awareness of my product and does it correlate to the price or the sales, first year sales. So if people are really aware of my product, are my sales going to go up? And an R value of 0.96 means the dots are really close to that line. So our script says when our R value has been calculated, we can square it and we can give meaning to that number right there. It means that about 92% of the variation of the information on Y can be accounted for by the least squared regression line of X on Y. And this script is what has to go on your paper. It's been a long time since we practiced this script, but we'll continue to practice it because the next chapter is back to least squared regression lines. So we will loop back on anybody that has forgotten this stuff. All right, we got time for one more and then one more video and we'll be done. This one's kind of a gimme. I like this one. Probably not a lot of people missed it, but it says the final grades are approximately normal, so we immediately know, aha, approximately normal. We have a mean and a standard deviation. So we say to ourselves, I should be able to use my normal CDF, and I might be able to use my inverse normal. So let's decide which one I want. It says, what is the approximate max grade somebody could obtain and still get an F? So it looks like an F would be for the bottom 10%. Okay, so if you knew exactly where the edge of the bottom 10% was, then you could figure out the score itself. Now I went a little crazy with the highlighters, but I just want to point out it's late. I'm a little tired, but it's fun. It definitely shows you what's happening here. So our data is approximately normal. Our mean is 76, and our standard deviation is 8. So if I add up, I go 3 standard deviations over, and if I subtract 8 3 times, I get over here. And so here's the distribution of the grades. And I want to know the area. Oh no, I already know the area under the curve to the left. If only 10% got Fs, then the area under the curve to the left is 0.1. And when we know the area under the curve to the left, we can use inverse normal with our mean and standard deviation. So that would be a grade of 65. And actually my picture doesn't look very much to scale because it would have landed somewhere in there. But I got 65.75 when I used this in my calculator. And that was choice C. Thanks for joining us.